Thank you. Right, so thank you so much for having me here talking about the science collaborations. I am the co-chair of one of the science collaborations, the Transcends and Variable Star Science Collaboration, as well as I've been serving as science collaborations coordinator for the past 2 years and some. And so I am involved in the Rubin Observatory explicitly on the science collaboration side. I have a lot of background in these slides, both about the Rubin Observatory, since this is the first talk of this meeting in a meeting, as well as particularly about the science collaborations and their activities. If you ask questions in the chat, I will try to see if I can monitor it. And if I can, I may redirect some of the background. So if you feel like there is too much background, let me know on the slides, on the chat, and I will try to adjust. So first of all, it's still a recent thing, so I will explicitly state when I refer to Rubin Observatory and when I refer to LSST. The Rubin Observatory used to be known as LSST, the Large Synoptic Survey Telescope. It got renamed in honor of Vera Rubin, one of the most visible women astronomers, and we are quite proud of that renaming. So we refer to Rubin Observatory as the facility, which includes the observatory, which, as you see here, it's under construction. In fact, this picture is a few months out of date, and now the dome does look more finished, although, of course, construction has been interrupted due to the pandemic recently. I will also refer to LSST, and when I refer to LSST, I mean the Legacy Survey of Space and Time, which is the survey that the Rubin Observatory will undertake in the first 10 years of its operations. And so this is the nomenclature and how I will use the 2 words as best as I can remember to be accurate. So the full pitch is that for the first 10 years of operation, the Vera C. Rubin Observatory will perform the Rubin Observatory Legacy Survey of Space and Time with the Rubin Observatory camera and the Simone Survey Telescope. I'm going to argue that the Legacy Survey of Space and Time is a truly transformational survey for a number of reasons. And particularly, I will highlight 3 reasons. The first one, perhaps the most obvious one, and the one that is most talked about, is the incredible increase in data volume that the Legacy Survey of Space and Time will generate compared to any precursor surveys. It's easy a factor of 10 in data volume increase from any survey that you may think of or they may be addressed as precursor surveys like ZTF. And it's nearly a factor of 10 from the Dark Energy survey, which delivered 2.5 terabytes of data per night. LSST will deliver about 20 terabytes of data every night. Not only will deliver 20 terabytes of data every night, but the complexity inherent in these data due to the high resolution, the high magnitude limit, and the high temporal cadence of the survey are really unique. Here is an image of a field that's seen by SDSS, and if my animations work, this is how an HSC, which is an LSST-like image of the same field would look with the LSST resolution and at the LSST depth. However, keep in mind that the Rubin Observatory will also observe, the LSST Rubin Observatory will also observe the entire Southern Hemisphere. So it will have this kind of image resolution and image depth. At a cadence of a few images, of an image every few days and multiple images per night, even over 18,000 square degrees at least of the Southern Hemisphere sky. Perhaps I study supernovae primarily, and so perhaps for me, one of the ways to take this point to make this point more obvious. Sorry, I'm trying to remove the window because I don't see my own slides, and that's tricky. Is to look at the number of supernovae that the survey will discover. On the left side, you have a plot of supernovae that have been discovered historically, the rate at which supernovae are discovered. And ZTF has definitely determined a dramatic increase in the last year or so. But the amount of data that LSST will produce, the amount of supernovae that LSST will see is dramatically higher, dramatically higher than anything that preceded it. And so I want you to think of it as a transformational rather than an incremental change in the delivery of data. There are 4 science teams that LSST will pursue. This really, the way you want to think about this is that LSST has been designed to pursue 4 very different science goals. And by that design, the design of the survey has been stretched to be able to do a variety of things. LSST will discover solar system objects from killer asteroids. It will discover the most distant explosions. It will cover 20 orders of magnitude in distance and 60 orders of magnitudes in energy scales. The science drivers are solar system, discovery of objects nearby and far away in the solar system, the study of the Milky Way and local volume by resolved stellar population. The survey will collect data for 20 billion galaxies and 17 billion stars, which will be characterized in shape, color, and variability. It will advance our knowledge of dark energy and dark matter through a variety of probes, including weak lens in large-scale structure, clusters of galaxies, and supernovae. And the one that is most dear to my heart and to some of the aspects of AGN science, it will explore the transient and variable universe with a stream of 1 to 10 million events every night. This means a stream of 1 to 10 million pixels or clusters of pixels that have changed since previous observations of the field. So they have changed compared to a template image of the same field. There will be about 1 to 10 million events detected and transmitted to the community within 60 seconds of observations. Here, the community is the entire world. This stream of events will be entirely public, but it will be served by brokers that will have a customer base. I won't dwell further in that, if not to mention the work that the science collaborations are doing towards the brokers. The third reason why LSST is very different from previous surveys is that the structure of the working teams, of the people that will do the science, the organization of the teams that will do the science, that will pursue science with the LSST data is really different from anything that happened before in astronomy. The Rubin Observatory, the members of the Rubin Observatory are supported by NSF and DOE to create the survey, create the pipeline that will produce data products from the survey and distribute those data products. They are not supported for doing science with those data products. The science will be produced but entirely by the by scientists worldwide in areas that have data access. If we're talking about static sky data and worldwide, because the alerts will be public if your science is alert-based. And particularly, there are 8 teams of scientists for a total of over 1,500 scientists that have recognized the importance of the legacy survey of space and time and have worked for, in some cases, many years, upwards of 10 years, to prepare for the survey. They're organized in 8 science collaborations. The science collaborations typically cover the domain, are aggregated based on the domain and expertise that the science within it have. For example, the Transient and Variable Star Science Collaboration, which I co-chair with Rachel Street, or the AGN Science Collaboration. There are 8, so Transient and Variable Star Science Collaboration, Stars, Milky Way and Local Volume, Dark Energy Science Collaboration, Solar System Science Collaborations, Galaxies Science Collaborations, AGN, Strong Lensing Science Collaborations. Those are all domain-based science collaboration, and ISSC, the Informatica and Statistics Science Collaboration, which is not domain-based, but rather collects experts and people and enthusiasts about methodology and machine learning and statistical methodology applied to to astrophysical data. And therefore it can serve as a support network for all the other science collaborations in the reduction of the data and the exploitation of the data. The science collaborations are truly form a very complex network because members of one science collaboration can belong to more than one science collaborations. This is a network diagram of the science collaborations where the chairs are identified by larger dots, and each dot is a person, and the connection represents the co-membership in multiple science collaborations. AGN is at the top right. It's not one of the largest science collaborations, but it has very many links with many other science collaborations, including particularly DESC, galaxies, stars Milky Way local volume, and TVS. It's an international organization. We cover 6 continents. As of now, the members, people that can participate in the science collaborations, if they have data rights because they live in the LSST Rubin Observatory, rather, data rights universe, which includes the US and Chile entirely. But many countries have worked towards acquiring data rights to the Rubin Observatory data. And many of those countries have also participated in the science collaborations. Let me talk a little bit more about the survey itself. I just left a slide here with some characteristics of the survey. I'm not going to go through any of those, if not the field of view, 9.6 square degrees, 6 filters, and a depth of about 24 to 25, depending on the filter for a single visit, and 27 for the full 10-year survey once the images are co-added. The survey will deliver a variety of data products. I already mentioned that it will deliver alerts, up to 10 million alerts per night, identifying objects in the sky or phenomena that have changed in brightness by more than 5 sigma. These images will also be reprocessed and delivered to, the original alerts are word public. The images will be reprocessed to deliver alert packets that are enhanced with further attributes and a history of variability at the location via force photometry, and delivered to the data rights holders 24 hours later. And finally, every year, after 6 months from the beginning of the survey, and 6 months after, and then every year after that, there will be a data release of static sky data products, which includes catalogs for all objects. Static sky is a little bit misleading because the catalogs are also for variable objects and include the variability metrics, as well as templates for the templates obtained by stacking the images. Obtained up until then. These data will also be proprietary. And so I want to highlight that what the Rubin Observatory and the LSST in particular are attempting to do is really ambition. They're attempting to surpass most surveys in both depth, spatial resolution, and temporal coverage. So while other surveys, precursor surveys, have pushed into one or maybe two of these directions, pushing into all 3 of the directions is quite difficult. One of the crucial things that will enable delivery of science through the LSST will be the definition of the cadence. Even though the cadence is in broad strokes defined by the requirements of exploring the transient skies, probing dark matter and dark energy, etc., the details of the survey, so how often will you actually revisit a field? Will you revisit it with the same filter? How often will you revisit it with the same filter versus another filter? Are really crucial to delivering science goals. And I want to point out that because LSST is trying to pursue a variety of science goals, this is a particularly difficult problem because some of those science goals will inevitably be in tension with others and require and require cadences that may impair science in other fields. Particularly, AGN has requirements, as I understand it, not being an AGN person, has requirements of both wide as well as regular and somewhat dense cadence. So I'll revisit this in a second when I talk about observing strategy proposals. Let me focus on three primary science collaborations activities. The science collaborations have been crucial in helping defining the LSST strategies, to which I was just referring. So this is a proposed footprint for the Rubin Observatory LSST. The Rubin Observatory LSST will attempt to cover a large swath of the southern hemisphere sky, upwards of 18,000 square degrees. Roughly every location in those 18,000 square degrees will be covered about 800 times. And this will fulfill sort of high-level requirements to pursue the 4 science goals that I discussed. However, optimizing this strategy has been a challenging activity that requires synergistic development and understanding of what are the different tensions and the tension that are generated by trying to pursue different goals and resolve them to generate a survey that really enable the most science. This is one example of how the science collaborations have contributed to this. This live document is called the COSAC. It is a live document that identifies proposals for observing strategies as well as metrics to evaluate the power of a particular observing strategy to pursue a particular science goal. And I know today you will have some time dedicated to developing, analyzing these metrics. So what this means is that a footprint that looks like this may actually in reality vary quite significantly. I also want to point out that when I refer to the survey, generally I'm referring to the wide, fast, deep survey, but that's only going to take up about 80% of the LSST survey time. Notice that on the right, I have the pre-pandemic dates for the survey, 2022 to 2032. And I have no information about the post-pandemic dates. The rest of the time, the roughly 20%, and that 80% may vary depending on the detail of the survey again and how efficient it is, will include other surveys, such as an Earth ecliptic survey or a galactic plane survey or a South Celestial Pole survey. These are just some of the proposals, as well as importantly for AGN science, at least for deep drilling fields. I'll get back to this in a second. One of the activities that the science collaborations have been very involved in the past couple of years is proposing cadences through a white paper submission, which happened in November 2018. Those cadences also proposed metrics, some of which have been implemented directly by the authors of the paper, some of which have been implemented by the Rubin Observatory team. And when I say metric, I mean a way to interact with a simulated database of LSST observations and extract numbers that measure the ability to pursue a specific science goal via a Python API called the Metric Analysis Framework. AGN contributed to 6.7% of the papers that were submitted in that cadence. This number is a little bit misleading because this is only the number where AGN was leading the submission, but they also contributed to a number of other papers. On the right-hand side of this, on the right side of this donut chart, you see a core diagram that shows that the papers were submitted by authors that straddled many science collaborations. So there the color is the same as on the left. So you can identify AGN by the, I guess, sepia color, I'm not sure. And you can identify links between the authors of the various AGN submitted and other submissions.
Federica, just about 2 more minutes.
Okay, so this may change the cadence quite significantly. So these are all a variety of proposed cadences. Let me skip forward. a number of, and the science collaborations have to design data products and generate that will be following the default data products that the Rubin Observatory will deliver. And so they're doing that. I want to mention a couple of things that I think might be particularly relevant to AGN, the blending and morphology. For example, with deep learning, this is just one example of the approaches that have been pursued by members of the science collaborations. Deep blending obviously is a particularly important topic for AGN. Photometric classification, there has been a huge effort in this field that really determined significant advances in the field in the last couple of years, led by DESC and TVS with the Plastic Astronomical Classification Challenge, a challenge that was delivered on Kaggle. Understanding the full workflow of transient science from discovery with a discovery engine like the Rubin Observatory through follow-up observation, and organizing these follow-up observations and automating them has been a focus of TVS. Obviously, one of the main problem in transient science that the survey is going to have is classification, because spectroscopic facilities will be vastly overwhelmed by the LSST data. And this is also, discussing this is also a focus of the science collaborations. Some other preparatory activities, particularly focusing on AGN. AGN has been far and above all the other science collaboration working towards collecting synergistic data sets at all wavelengths, and they've been largely responsive. And I know that this slide should be updated, because I think the coverage on these particular fields, which are 4 of the deep drilling fields, has even improved since this. And they've particularly, let me skip a couple of slides, they've been particularly instrumental in collecting data at all wavelengths for the deep drilling fields that have already been selected, and in cementing the selection of those deep drilling fields because of the synergistic data sets. The last thing that I want to mention is, well, obviously there's a lot of committee work, etc. But the last thing that I really want to mention, particularly at this time, is that as I've been the science collaborations coordinator for a couple of years now, I want to shift my focus in the next couple of years to particularly thinking about diversity and inclusion. Astronomy is, as of yet, not inclusive. These are data from the NSF that indicate how many astronomy and physics and astronomy PhDs are obtained every year. Black males, and particularly Black female, are in the single digits when approaching 1,000 PhDs per year. And there's just no other way to say this. This is not okay. So I want to focus on that more. Some of the activities that this will involve is formalizing efforts to assure that there are considerations about climate diversity and inclusions within the structure of the science collaborations. The science collaborations are an independent body, so there is no oversight. So we need to impose oversights ourselves if we want to push this agenda. This will include creating committees for climate diversity and inclusion of the science collaborations, and creating educational opportunities. For example, and I swear this is the last thing I say, we have proposed through the Enabling Science proposal by the LSST Corporation, we have proposed for an anti-racism workshop to be held at the PCW 2021, hoping that this will be in person, because these kind of activities are most effective in person. And together with that, the creation of roadmaps for the science collaboration towards diversity and inclusion that also include metrics for accountability. And that's all I wanted to say.
Great. Thanks a lot, Federica. We just have just a couple of minutes for a couple of questions. I'll read them to you if that works.
Mm-hmm.
Okay, so the first question that we've received asks, someone has been following the controversy about the impact of the SpaceX Starlink satellite constellation on the Rubin Observatory. And the person is asking if you are satisfied that the Starlink system is going to have minimal impact on LSST, and do you think you'll have sufficient influence with SpaceX to guarantee their cooperation?
Okay, that's a tricky question. So I'm not personally satisfied. I don't think there is. I don't think there is any evidence that they will have minimal impact. There is definitely a concern that the impact would be significant. I personally don't have the authority or the influence that you refer to, but definitely the Rubin Observatory leadership, well, Tony Tyson in particular, has embraced this as a priority. They're just organizing a workshop now that will include both Rubin members, science collaboration members, the community at large, as well as members of the companies that are launching the satellites, to negotiate with them attempts to mitigate the issue. The issue continues to be a difficult one.
Okay. One other question quickly. Someone asks, will there be a pipeline for star-galaxy separation? And can you give a couple details about that?
So there is a pipeline for star-galaxy separation. There is a lot of work on deep blending and galaxy-star separation. Particularly, one of the main models that is being used is known as Scarlet, which is a deep blender, and it's under continuous work and improvement. And this would be the official pipeline. So what this means is that this would enhance the ability of the Rubin Observatory to produce accurate catalogs of stars and galaxies. In addition, as I mentioned, there is a lot of work going on specifically within each science collaboration to produce and augment this to produce alternative pipelines and augment this pipeline for specific needs. And as I said, including some cutting edge technology approaches that include machine learning and deep learning, etc.
Okay.
I don't have no technical details. That is really not my domain of expertise.
Okay. Given the time, I think that covers all the questions. One other person did ask if your slides will be available online. And I will say, yeah, the AGN Science Collaboration hopes to post all of these slides on the AGN-SC webpage when all is said and done. It may take a week or two, but we'll get them up there. Yes. Okay, thanks a lot, Federica.
Thank you.
Gordon, do you want to take over as chair temporarily now?
Yeah, so Neil, before you start, let's make sure everybody knows to submit questions to the Q&As. Zoom webinar is a little bit different than a Zoom meeting in that the Q&A is for questions and the chat is basically internal for the speakers. And so Neil's going to introduce the AGN Science Collaboration.
Okay, so yeah, today I would like to review briefly the LSST Active Galaxy Science Collaboration. Hopefully this will be both a useful review for the current members, as well as encouraging interest from AAS folks more generally. Among the AGN Science Collaboration, we are interested in essentially all aspects of AGNs. We have people interested in the immediate vicinity of the black hole and the accretion disk. We have people working on the emission line regions. We have people interested in the obscuring materials. We have people interested in the jets, in host galaxies, and in black hole galaxy coevolution, and even in the role of active galaxies in large-scale structures. And so we are taking a broad-based interest in all aspects of the AGN phenomenon. The overall outline for this talk, I'm going to start by briefly covering the nature and the history of the Active Galaxy Science Collaboration, and that will relate to some of the things that Federica just told us. I will then mention some recent and ongoing activities, and then I'll end, if there's time, just talking about some prospects for future meetings. I'll start with the basic nature and history. So the AGN-SC has a few overall goals. The big one, of course, is just to maximize the overall active galaxy science return of LSST. And we also want to, as part of that, give feedback to the project to ensure that when they're making choices about the project, that nothing that would compromise AGN science would happen. We want to ensure that excellent AGN science will be possible. And then, of course, as part of this meeting, for example, we also want to educate the broader community about LSST AGN science and the opportunities there. So the Active Galaxy Science Collaboration has existed since fall 2006, and it has always been, by design, distinct from the project. And here is, in fact, one of the original emails from when the science collaborations were being set up. I did a deep dive into my old email archive to find this. And here, in fact, is one of the original defining documents for the science collaboration prepared by Steve Kahn, who's currently the director. And it sets up the science collaborations as having clear overlap with the project, but also being significantly distinct. And for example, we are distinct in the sense that we have never received any direct funding from the project. And that has been one of the challenges we faced, although I think we've managed to remain pretty effective nonetheless. Now, for many years, the Active Galaxy Science Collaboration worked as a kind of loose confederation where people were sharing information, they were collaborating from time to time on things that were highly relevant to LSST. But over the past couple of years, as operations have approached, it has been working increasingly as a more formal collaboration. I'll say more about that in a minute. And again, at least in the United States, at least right now, funding for the huge work required does remain a major challenge, but we are doing our best. Here is the current rundown on the membership of the Active Galaxy Science Collaboration. We currently have 70 members distributed across countries as listed here. And as of 2019, where we did a significant reorganization, we now have a tiered membership structure and a formal charter, which you can review on the webpage for the Active Galaxy Science Collaboration, which is here if you're interested. We currently have 61 associate members. Those are people who are interested and want to remain informed and want to have dialogue and input. And then we have another level of full members. These are people who have committed to doing a significant amount of heavy lifting to keep the science collaboration functioning, as well as to do a lot of work on AGN science. And then there is a core membership, which no one has achieved yet, which involves publication rights and things of that type. The membership applications are welcome. For the AGN science collaboration, at least, membership applications are welcome even for people who presently lack data rights. In fact, some of the people from these countries here presently do not have data rights. They are applying for data rights. And application instructions can be found, again, via the AGNSC webpage down here. Here are just a couple of photos to show you that we're all friendly people. This is from a 2017 January meeting. This was, I think, was the largest meeting to date that the AGN Science Collaboration has managed to pull off. This was run by Ohad Shemer, was the lead organizer. And there were lots of good discussions and such at this meeting, and all the talks from this meeting, in fact, are available on the website. Also lots of nice barbecue dinners and stuff down in Texas that we got to enjoy. And here is the overall organization of the Active Galaxy Science Collaboration. So we have, of course, the chair level, that is me presently. Then you have a number of panels that keep the various aspects of the science collaboration functioning. We have a membership panel that reviews new membership applications. We have a publications panel, an ethics panel, and so on, as listed here. And then we have a number of important sort of science-driven groups. We have a selection classification group, a photometric redshift group, a variability science group, and a follow-up group. These, again, are discussed in the AGN charter and such. This whole document's this whole image is from the AGN SC charter. And you will hear about some of the work that's been ongoing in the science subgroups in the coming talks. Okay, so now I just want to say some words about some recent and ongoing activities. First of all, we do have a number of ways that we remain in effective communication. We have regular full Active Galaxy Science Collaboration and subgroup telecons. We have in-person and now remote meetings occasionally. We have an email list. We're involved, we are members or plugged into the LSST community discussion forum, and we also have a Slack channel. So those are the various ways that we stay in communication. And we have gone through an exercise where we in an organized way determined a lot of the main science we wanted to pursue, and then we prioritized the main tasks that will be necessary to achieve to do that science. And you can read about those things in this AGN Science Collaboration Roadmap. A second version of this is in progress. It is intended to be a living document. And so if upon reading this, you think that something critical has been left out, feel free to contribute to this document to help make it better. We're working on this at present, and again, all the time, practically. Now I want to say a few words about one of the key contributions that's ongoing now. This relates to what Federica mentioned about how the survey strategy for LSST is going to be critical in achieving AGN science. And so we want to make sure that AGN interests are represented there. And so broadly, there is this currently ongoing survey strategy optimization process. Federica referred to this. Its overall goal is to determine how to observe the main survey and then spend about 10 to 20% of the time on mini surveys. A number of possibilities are here. This is clearly essential, again, for many AGN science cases, making sure that we can do general variability science, making sure we can do proper AGN selection, making sure we can study supermassive black hole transients and so on. And so, as Federica mentioned, the AGN Science Collaboration contributed a couple of white papers as part of this survey strategy optimization process. These were due, if I recall, back in November of 2018. Here are two of them. I led one on the deep drilling fields, where I tried to talk about what the best choices of footprints would be, what the best choices of cadence requirements would be, and what the needed total depth requirements are for the deep drilling fields. Here's another one that Gordon led. Gordon led one where he explored the effects of different main survey cadence choices on AGN selection and characterization, particularly with reference to the rolling cadences that are broadly being discussed in the project, and tried to assess what rolling cadences might be acceptable for AGN science and which ones would likely be problematic. Now, presently, where we are in this process is the project is currently taking the inputs from those science collaborations and running a large number of operation simulations to determine which of these things can be technically achieved. And then furthermore, the project has just set up this Survey Cadence Optimization Committee, which is an extremely important committee that will be making the real hard choices about cadence in the coming months to perhaps year and a half perhaps. And so one thing that will be essential will be to make sure that the AGN Science Collaboration is effectively interfacing with this committee, because we definitely need to get the cadence right for AGN science. And so there's a number of ways that we can do that. First of all, so to interact effectively with the Survey Cadence Optimization Committee, we need to work through the available operation simulations to assess if these indeed allow the desired AGN science to be achieved. And we are working on that presently. My group here, for example, has been doing quite a bit of work on the deep drilling fields. I know the Drexel folks have been looking at a lot of wide, fast, deep issues, and other science collaboration folks are getting started plowing through the large amount of effort, a large body of simulations that is already available. And then the next step will be to, informed by the results of these simulations, will be to produce so-called metrics that evaluate the performance of a given LSST survey implementation in achieving your desired science goals. And so one thing that we will be discussing in the discussion session on June 3rd will be these metrics. We decided to focus a lot of that June 3rd afternoon session on metric discussions. And so again, I've asked all of the talk speakers, the science talk speakers, to present their ideas for metrics in their talks. So you will hear them from time to time referring about metrics. They're referring to these issues here. And so again, you'll be hearing quite a bit more about these metrics, which again will be ultimately used to define in a clear quantitative way whether AGN science of interest is indeed being achieved properly by the surveys as currently envisioned. Okay, some additional important activities of the AGN Science Collaboration. Well, we continue to serve on broader LSST committees. For example, the AGN Science Collaboration is currently supporting the work of the so-called Contributions Evaluations Committee, which is assessing presently which international partners will earn data rights. Zhao Fan is the lead person on that. We also recently contributed to an ad hoc committee that assessed community needs for access and on what timescale to the pixel level LSST images. Gordon Richards did work on that. And then we plan to interact substantially with the so-called Rubin Euclid Joint Data Products Working Group, which will be trying to come up with a set of joint data products which will be available to all the members of the Rubin and Euclid teams. Okay, and so we have put forward suggested members for that working group as well. Now, Another thing that we are doing, of course, is we have a lot of interest in preparing, well, students and postdocs, and along the way, of course, ourselves to achieve AG in science. And so we have recently, very recently, last week, I believe, proposed a so-called AGN data challenge to the LSST Corporation. And this would be a data challenge with the goal of motivating planning for AGN science, and would focus on a few key issues: parameterization of AGN light curves, AGN selection, AGN photometric redshifts. This would be done in a data set, very likely the XMM LSS field, which will be one of the LSST deep drilling fields, and which already has a lot of valuable complementary data that can be used to prepare for LSST. And so this is another important ongoing effort, and we're hoping these types of efforts will be able to be supported by the LSST Corporation. We also regularly give talks worldwide highlighting LSST AGN science. These are just images and announcements of a few of the talks where the past couple of years, meetings of the past couple of years where we have given talks presenting LSST AGN science. So there's a lot of information that we do, a lot of effort we put forward trying to share this information with the broader community. And then finally, as Federica mentioned, another, I think, big contribution to the AGN Science collaboration has been gathering broadly useful multi-wavelength data. And of course, this is motivated by the fundamentally multi-wavelength nature of active galaxies. LSST, of course, covers this band here of the electromagnetic spectrum, but of course it would be crazy to try to study AGNs only with that. The best science will be done by combining LSST, which will be operating in this time frame, with all the wonderful radio data and infrared data and spectroscopic data and X-ray data and such. And with all of those things together, as we'll hear about later on, we hope to select something like 50+ million reliable AGNs, reaching all the way out to very high redshifts indeed. So what has the AGN Science Collaboration achieved in this regard? Well, there's been a lot of effort that we've put forward in the deep drilling fields. We have, Mark Lacey, for example, has led efforts to gather a lot of excellent Spitzer data across the deep drilling fields. That way, when LSST switches on, there will be already the best possible infrared data in the can, ready to go to be used in conjunction with the LSST data. And we're very grateful for those efforts because, of course, Spitzer is no longer with us. And so this had to be done before LSST actually switched on. We have also at Penn State and with collaborators worldwide have been gathering X-ray data across the deep drilling fields. We have already covered the XMM LSS region. We are nearly done covering a wide region around the Chandra Deep Field South, and the Elias S1 region is currently much covered as well. We're mostly done with that region. And so there we expect to detect something like 12,000 AGNs, and this will serve as a ground truth X-ray selected AGN sample for calibration of LSST AGN selection. And Qingling Ni, I believe in the session this afternoon, will be discussing this further. I will end then just very briefly, because I suspect time is short, by discussing some future meeting prospects. If this meeting goes well, this remote meeting, we actually may like to have some further meetings. While clearly Zoom is not perfect, these Zoom meetings do have the advantage of being highly economical, which is good given that the AGN Science Collaboration presently has almost no funding. And so, you know, one thing we would perhaps like to do would be to have an annual summer AGN SC meeting via Zoom, especially if this one is deemed to be successful. And so let's, in the afternoon session on June 3rd, consider and discuss this further based on our impressions of how this meeting has gone. And with that, I will stop. So thank you very much.
Okay, so we have plenty of time for questions.
Okay.
Couple have been asked and answered in the chat.
Okay.
And I'll let people keep asking them. So one person, Neil, I mean, you can just look at these yourself too, I suppose, was asking what the next steps are.
Okay.
Quite sure what is meant there, but I guess,
okay.
you know, how can people get involved?
How can people, okay, there's a number of things. So the next steps for the science collaboration, well there are many. It's going to be continuing to gather supporting multi-wavelength data, executing these data challenges and such to build ourselves up to deal with, the types of data we'll be having from LSST. And then in terms of getting involved, let me back up. So the science collaboration is certainly welcomes new people to join. And again, that's even from people who lack data rights. And so anyone who has interest is welcome to join. And you can then start, if you feel, for example, that, let me just jump ahead, if you feel that your interests are not being properly represented right now in the roadmap, you can help improve the roadmap. That would be one immediately valuable thing. And there's a number of other possible ways that one can get involved. If you have expertise or connections with a particular multi-wavelength facility or spectroscopic facility that would likely be important in following up active galaxies that are found by LSST, that would be a very valuable thing you could plug into. And there's many other possible ways people can plug in. These white papers are mostly done, but certainly another immediately valuable thing would be to start working through the available operation simulations. If you want to be sure that LSST will allow you to execute the science that you're excited in doing, this is the way to make sure that will indeed happen. So those are a few possibilities. I'm certainly always happy to chat with people who may have interest more broadly as well.
Great, thanks, Neil. So I want to make sure that people also see the questions that were answered online. So somebody asked where the Cadence white papers are, and Federica put a link to that in the answer.
So that's
question.
Already good. Okay.
And then Paolo Coppi asked about results from plastic and Kaggle, and I said there, people were required to post solutions to that, but I don't know, and I'll try to find a link for that when we're done.
I can answer that. I can answer that a bit if you want.
Go ahead. Yes.
There are papers that describe the challenge that are already published. There are papers that describes the result that are under review. We're specifically reviewing the comprehensive paper that will describe the results right now.
Okay.
And then Neil, Il-Sung Yoon is asking about major funding for the science collaboration as a whole. I guess how we might go about securing that.
Well, that is a broader issue. The natural agency that would typically do this kind of thing would be, the National Science Foundation. And so outreach to the National Science Foundation, showing, first of all, that we're achieving valuable things right now, and then explaining what we would like to achieve in the future. Hopefully that can lead on a pathway toward funding. Clearly, funding is very challenging across the whole astronomical community right now, but hopefully some funding can ultimately be secured to be sure that the science that will be enabled by the enormous investment already made by NSF and DOE can actually be achieved. So outreach to the NSF is one valuable way to do that. And there are broader NSF proposals, proposal mechanisms by which one can propose for networks type proposals, and one of those has been put forward right now. Federica, you can comment on that if you wish.
So we are pursuing large proposals. We are pursuing smaller proposals through the NSF. Obviously, I would say that historically, the NSF has been the kind of agency where it's hard to get funding for preparatory science, unlike more space-focused, for example, agencies or agencies that work on physics experiments rather than astrophysics. It seems to me fair to say that the NSF has been a little bit more short-sighted than these other agencies. And I also want to mention that there is an external body, the LSST Corporation, which is a nonprofit which is designed to support the science that will come from the Rubin Observatory and the LSST. And they've been working towards supporting the science collaboration. They're really the only body that has consistently provided support to the science collaborations. As of now, the support is not huge. It's about, on average, maybe $200,000 a year that supported meetings, activities like the plastic challenge. But they are also fundraising for much larger and impactful activities for the science collaborations and for the member institutes, their member organization.
Yeah.
But the members and the science collaboration strongly overlap.
Yeah, and I'll just say just one or two more words. So presently, various people in the AGN science collaboration, and I'm just speaking from the United States perspective. Of course, there's a whole broader international perspective as well. But just within the United States, some people have managed to find some funding by doing this complementary multi-wavelength work. I mean, gathering all these XMM observations, gathering all these Spitzer observations, that has some funding associated with it. And of course, the idea here is you do immediately valuable science with the Spitzer data or the X-ray data that you already have in hand, and then you're also building toward LSST along the way. So that's another approach. And then, of course, another approach some people have taken successfully have been to get funding to execute immediately important science with say, pan-stars or with dark energy survey or with hypersuprime cam. And those, of course, again, allow exciting science to be done right now and are naturally building toward LSST. That's another approach that people are taking to get some support. Any other questions, Gordon? Are we good? Hello?
Oops, sorry.
Oh,
I don't see any more, but we do have a few more minutes if people want to ask more questions.
I'm good. It's fine. I can move back unless anyone. I'm certainly happy to take questions, but we can go on to your talk just to be sure we'll be able to end on time. I haven't been able to follow the schedule while I was speaking.
There is a question. Sorry,
go ahead.
there's a question about the success rate for the Enabling Science proposal. I can answer that very briefly.
Go ahead.
Typically, the success rate is high, especially if the proposals are organized from within the science collaborations to support known needed activities like meetings, etc. Also from inside the science collaboration, we can strategize with the corporation to make sure that more proposals are accepted, like for example, organize synergistic proposals that involve more than one science collaboration. But it really depends on the fundraising activities, which can largely vary from a year to the next.
Yep. And yeah, Federica is right. I mean, in addition to the AGN SC leading this proposal, we are also supporting a couple of other enabling science proposals with galaxies and lensing folks and things like that. So hopefully all of these, I think we're all going to have to work together to get there. So. Okay, well, if we're good, then I can take over as chair again, Gordon, and I will stop sharing my screen.
Okay, great.
And you can, let me just stop this here, and you can start your talk.
Sounds good.
Okay, so while Gordon gets set up, I will just say that we are now, we've now covered these two introductory talks on the science collaborations and the nature of the AGN science collaboration. We are now going to go into a set of science-focused talks, of which I believe then there will be 14 over the next several sessions, again, running June 1st, 2nd, and 3rd. And everyone is, of course, welcome to attend and all of these science talks as well. So the first one of these will be given by Gordon Richards, and I believe it will be on AGN selection using multiple data types. So go ahead, Gordon.
Great, thanks, Neil. All right, let me see if I get this computer set up. All right, sound okay?
Yes.
Okay, great. Okay, so I'm going to talk about the training sets that Weizhang, you and I at Drexel are starting to build for LSST AGN selection and PhotoZ, and tell you about some of the things that we need help with from the broader community. So in addition to the talks being recorded, I've included annotated slides at the link shown, and then also the GitHub that Weizhang has developed for people to learn how to access the training set. And additionally, the AGN Science Collaboration's roadmap document. As Fed said, LSST is now the legacy survey of space and time, being conducted with the Simonia Survey Telescope at the Vera Rubin Observatory. It's a joint project of NSF and DOE. And while SDSS took over 8 years to observe 8,000 square degrees, we're now able to do that basically every 3 days or so. And so I want to start with the basics of the survey, which Fred touched on a little bit, but make sure everybody sort of understands the relevant things for the AGN Science Collaboration. We're making observations in U, G, R, I, Z, and Y to about 24th magnitude in a single epoch. But co-adding something like 80 to 200 images per band to get to 27th magnitude overall. We're observing the entire southern sky with 4 to 10 fields that are the size of the LSST field of view, about 10 square degrees. That they're going to be something like 10 to 100 times deeper. It'll be possible to select AGNs both from the alerts and from the yearly data releases with sort of different strategies for each. And as Neil and Fed both mentioned, I mean, one of the reasons to get involved now is it's not set in stone, right? So we have not decided on the final cadence, the final area, the final depth, or anything like that. So those are being simulated, and we're trying to optimize the choices for basically the overall science. And so in addition to the training sets I'm talking about today, we have tools for analyzing the OpSims, which are basically the simulations for trying to decide what cadence we're going to adopt. Okay, so LSST should identify about 10 to 30 million AGNs using data from LSST alone. It should detect something like 300 million AGNs. And then the difference between those things is because obscuration and host galaxy dilution will hinder the selection of some objects as AGN. So that is, LSST will have observed them, but that doesn't mean that we'll have recognized them as an AGN. And the hope is by combining with multi-wavelength data, infrared and X-ray in particular, we should be able to recognize about 100 million AGNs as such. And then the figure on the left illustrates why the X-ray data is so powerful. Unlike in the optical, powerful X-ray sources have a very high probability of being AGNs. So this talk is mostly about the process of starting to construct training sets that can be used to develop algorithms that are needed to select AGN and LSST. As Neil said, funding is an issue, as it is for most LSST science preparation, but we did recently submit this proposal for internal funding, which would allow us to give prize money for a AGN data challenge. I'm hopeful that regardless of whether we have this funding or not, we'd be able to put something out for people to play with. Something sort of like the plastic Kaggle competition, but necessarily a little bit different in the sense that we don't really have truth tables yet. And so I'll say more about that as I go. So my philosophy in this process is that 95% completeness, efficiency, and PhotoZ accuracy basically might as well be 0. And that's because there's no spectroscopic component to LSST. I mean, 95% completeness, might be okay, but 95% efficiency would be devastating. And obviously, this is going to be different for type 1 and type 2 AGNs. And so I would say that taking advantage of all sources of data, types of data, are what we need to get us to something more like 99%. So there are many ways that LSST is rather different than SDSS, and we recognize that. But the way that we are starting this process is sort of from the SDSS perspective. Like, how can we start with SDSS data and build from there? We have no real intention of trying to get this right the first time. I see this as a process of building things up and tearing them down to rebuild. I've been saying for a while now that a great outcome would be people saying, hey, Gordon, you're an idiot. You should be doing X instead, right? And in many ways, that would be a fantastic outcome because then people are engaging. So the catch is, if you have a suggestion for doing X instead of what we're doing, then you're now in charge of X, and we're going to corral you into helping with that. But that would be great. Ultimately, our goal is to identify AGNs in all of the classes that are mentioned in the AGN-SC's roadmap. So that's unobscured type 1 quasars, obscured type 2 quasars, low luminosity AGNs, meaning things that are host dominated as opposed to central engine dominated. Transient supermassive black hole fueling events, that certainly includes things like changing look AGNs. So the plan is basically this. So in addition to colors and variability, which should be obvious, there's 9 or more different types of information that can be used for AGN selection. And so from the work that we're doing at Drexel, we're concentrating on type 1 sources for which all of this information in yellow is available from LSST alone, and concentrating on data releases. But that doesn't prevent us from excluding information that's not available for some types of AGNs or some areas of sky. So for example, type 2s, or where there's no deep X-ray data, or trying to identify AGNs in alerts. But that's the sort of data release type 1 objects worth a lot of information is sort of where we're starting. So I'd argue that if you find yourself trying to identify AGNs in LSST in the future, and you're not using all of these data types simultaneously, you're wasting information. However, everyone's not familiar with how to best use that information. And so part of the goal of this work is to help everyone include these data types in their analysis. And I'll spend some time talking about a few of them. So we're building training sets in 2 complementary regions, the so-called slow and striped 2 region on the celestial equator, about 300 square degrees, not all of which has multi-wavelength data, but a good portion of it. We're focusing largely on time domain. So a decade of time domain data from SDSS alone, and then also other surveys as well that have been engaged in time domain before and since then. And there's a lot of spectroscopic follow-up in that area as well. So that's the training set that is the start of which is currently available on GitHub, or at least the GitHub link will tell you how to get access to it. And then we are also developing a training set in the XMM LSS area, as Neil mentioned. So that's about 5 square degrees. That one is important because it's one of the deep drilling fields and has very deep multi-wavelength data, particularly in the X-ray, which is what we can use as sort of a truth table in the absence of spectroscopic coverage. So we're building the training set in JHU's SciServer environment, which is similar to what the LSST data portal will be in terms of bringing your code to the data. So the data are stored at Johns Hopkins, as are your notebooks. You're going to use SciServer's processes rather than your own. The software is largely all set up for you, so you don't have to learn sort of specialized things. So really, you just need a dumb terminal and an internet connection to get started analyzing the data and contribute to the process. So once the data have been gathered, I'd argue for starting kind of simple. So using decision trees is the first pass way to integrate different sources of data. So for example, your object may be in or out of the galactic plane. It may be variable. If it is variable, it may be periodic or it may be stochastic. Your object could be moving, it could be not moving, it could be extended or not, it could be a dropout object or not. And then the path taken will depend on the answer to those questions, depend on the data that's available and what properties those objects have. Better yet would be to incorporate the information from those features into machine learning code. However, for some of the data types, that requires some level of feature engineering. For example, if you have light curves, we need to parameterize those light curves somehow, measure the parameters, like a damp random walk is sort of the go-to, but there's lots of different ways to parameterize that. And so we have to figure out what parameters are actually going to go into the machine learning model. Instead of just asking whether it's moving or not, you might want to know, what the actual proper motion is. Instead of asking whether it's extended or not, you maybe want the Sursic index. Better yet would be, if we can, some non-parametric analysis. So here, Weizhong has illustrated experimenting with density maps. So this is a quasar on the right and a variable star on the left, where we've captured the entire light curve into one graph, and you could imagine basically throwing basically that plot into your machine learning code as a feature to analyze. So here's a simple set of color plots showing what's in the training set right now. Everything with this color scheme was made using the training set that's currently available, using notebooks that are available to everyone as well. So it's worth noting that the stars in the training set are really point sources that have not yet been identified as quasars, and includes sources fainter than the SDSS spectroscopic limit. So many of the stars are actually quasars, and one of the first challenges is to actually clean these out of the training set. As I said, we don't really have the truth tables for everything that we could possibly want to have. So using SDSS colors alone for existing training set objects and a simple random forest algorithm, we can get something like 91% completeness and 88% efficiency. So that's far short of our goal, and these numbers aren't meant to predict what LSST is going to actually do, just give you a baseline for how far color selection gets you for the rest of this presentation, and how much adding other information gets you when we include it. So to illustrate adding other information, I'm including here proper motion data from Gaia. In short, stars move and quasars don't. So over on the left, the dotted line that extends out to high proper motion, those are stars. The dashed line that doesn't get to as high proper motion and basically is consistent with the error are quasars. And on the right, I'm showing the histogram of matches between SDSS and Gaia. And you might notice that Gaia doesn't go anywhere near as deep as LSST, and so you might wonder how useful that is. But this is a really nice paper by Dustin Lang back in 2009, arguing that we should really be able to measure proper motion for even undetected sources like this high Z quasar from their paper. And that should prevent us from having to take spectra of stars that are masquerading as high Z quasars or follow-up photometry and things like that. So there's a lot of information in LSST that is going to be available to us. So when we add the proper motion, we get a small improvement, which looks like sort of a 1 to 2% gain. But I want to impress upon you that that's really a 10 to 20% gain relative to what's possible. That is, we got sort of 90% of the way there just by using colors alone, and we are only trying to get sort of 10% more. So every sort of 1 or 2% above 90% is really a big deal. But I would take these numbers with a grain of salt until we basically have a proper training set. Another source of information is differential chromatic refraction. In short, the different band passes are shifted on the sky by different amounts due to atmospheric refraction. Quasars change position more than expected, or in a different way than expected in the U and G band due to their emission lines. And how much they shift depends on both the redshift and the air mass. And so we can take advantage of that information. You can think of it as the same process as determining the proper motion, but instead of time being the independent variable, the air mass is the independent variable. So we currently don't include this DCR information in the training set because it's not clear how or even if the information will be recorded in LSST. But we're working hard to make sure that it is. The basic issue is this: for SDSS, we weren't trying to stack multiple epochs or not in general. And so it wasn't really important that the different band passes weren't lined up, and we just reported the position of the U band and the G band and the R band separately. For LSST, the need for stacking means that's not acceptable. And so it may be that the DCR information goes into the PSF and the astrometric solution in general, and possibly in a way that's never reported in a form that can be used as a feature. But I think everybody recognizes this is free information, both for classification and for PhotoZ, which Roberto will talk about later. And so we'd like to try to keep that information if we can. That leads us to a couple of metrics that we can use to decide which cadence is best in terms of how to take advantage of DCR. And we haven't figured out the details of that, but that's something that we can certainly start to be working on. Clearly, variability is going to play a crucial role in analysis for LSST and basically figuring out classifying different classes of objects. So that will obviously be very true for AGNs as well. And we have a number of talks in the next couple of days discussing the variability properties of AGNs, right? So, you know, some stars are variable, others are and maybe periodically variable, other stars are not very variable. Quasars are generally variable, but in a way that's different from stars, and we can also take advantage of that information. Here, I'm illustrating that the training set currently includes parameters for a damped harmonic oscillator fit to the light curve. So that's basically one level of complexity higher than a damped random walk. What we can see is from the different contours between the stars and the quasars, the stars vary differently than the quasars do. And the training set currently doesn't include non-variable stars. And so obviously, if you were non-variable, you would have even different parameter space here. And so adding the variability clearly improves the results. So we get, you know, another 2% in completeness and efficiency. And again, that's, you know, not 2%, but 20 to 30% of what we were trying to achieve. Everything up till now uses data only generated by LSST, or at least data that can be generated by LSST. Multi-wavelength data is really going to be a huge factor for us, basically leveraging us from 10 to 30 million objects to something like 100 million objects. And so here I'm illustrating some results by adding infrared data from the Spitzer SPIES survey on stripe 82. So you can see in the bottom right corner here, the quasars and the stars separate out really quite well. And in terms of the infrared parameter space, I haven't included galaxies in here, but obviously that's important as well. And so this is just illustrating how much the infrared data really does for us. Deep X-ray data will really be the ultimate test in the few regions that we have it, because of how it can be used as a sort of truth table. And I'd like to emphasize that we should really be thinking of things not in terms of multi-wavelength data, but synergies with other facilities. The reason being that some of the so-called multi-wavelength data will actually be in the optical UV as well, like Euclid data. So I've been pushing the idea of what I call data ambassadors for a while now, but I want to formalize that process today. And so what do I mean? What I mean is that we need people that are willing to be the AGN Science Collaboration's official expert for a given external data set. So I sat down before this talk to think about what I meant by that. And so this is what I think I mean. I mean that if you volunteer to be the data ambassador for WISE or UKids or Chandra Source Catalog or whatever, it means you are willing to generate a catalog for the Stripe 82 and XMM LSS training areas and produce metadata explaining what those features are, how the catalog was produced, basically, sort of what information is included and why, what the units are, what flags were used to produce, to reject bad objects, which is important, and things like that. Also give advice on matching constraints, half arc second, 2 arc second, and so on. And so what I mean is, you would run the UKID search, provide the details of the search, give advice on what the matching radius should be, tell us why and how you've gotten rid of bad objects and so on. But ultimately the catalogs aren't what we need. We need force photometry, which means advice on pixel level data. And so I hope people will enable us to do that as well. It's clear that with such a large volume of mixed data, we will need machine learning algorithms. The training set right now uses scikit-learn to produce examples, but we'll need algorithms and expertise really that go beyond that. It's highly likely that ensemble methods will be needed and multiple algorithms will be needed for different classes of AGNs. So for example, Redshift 0.7 quasars and Redshift 7 quasars might as well be completely different objects, and you can imagine completely different algorithms handling those. Ultimately, what we want to produce is one or more AGN probabilities for literally every object in LSST rather than making catalogs.
Just about 2 minutes, Gordon.
So I said at the start, we're taking an approach that starts with SDSS, but again, LSST is not SDSS, and there's lots of issues to consider. I'm not going to go through these in detail, but these are the sort of things that we want to look into. The depth, so for example, high Z sources are going to be extended in ways that they weren't in SDSS, and the majority of AGNs will look nothing like SDSS luminous quasars. Difference imaging is something that we need to get experience with. That is, thinking of AGNs as sort of more like a supernova, a kind of sources. It is sort of one way to maybe think about it. We need expertise in algorithms. We have a long wish list of properties that existing algorithms don't necessarily have. Very few machine learning algorithms handle errors in the way that we need them to. There are many algorithms that return probabilities instead of classes, but not necessarily the ones that we want to use. We want full PDFs for the photo-Zs. It would be nice to merge light curves from different band passes. So for example, treat the I band and the G band as perturbations of R band and triple the cadence of the light curve. Maybe something that's not really an algorithm kind of thing, but we want sort of one algorithm that can be applied to all of the wide, fast, deep, including the regions in the DDF, but then another algorithm that takes advantage of the DDFs. And so how to do this is an important thing to figure out. Okay, so in terms of resources, I calculated recently that I think LSST science preparation is short about $20 million per year. And the AGN Science Collaboration is no exception to that. Nevertheless, as Neil said, we're making progress, but slowly but surely. And any help would certainly be very much appreciated. I'm going to leave you with my contact information, the GitHubs for the LSST training set as it currently exists and where it will be as we start to build it. The GitHub for where we're doing the cadence simulation analysis on AGN-SC roadmap. Before I answer questions, I want to advertise Dara Norman's inclusivity revolution talk, which is going to start in about, I think, 15 minutes or so. Thanks.
Okay. Can you hear me, Gordon?
Yep.
Okay, so we have a few questions. I'll just go through them in order. The first one is from Michael Strauss. He says, you argue that you want to use all the data available to select AGNs, but you can get to the point that the selection algorithm becomes so complicated as to be difficult to model and even quantify in order to understand what your level of completeness is. And so could you comment on the challenges there?
Yeah, I guess the way I see it is, you want to run one sort of fairly simple algorithm on the whole sky that doesn't require any multi-wavelength data or anything outside of LSST as sort of a baseline, and then sort of build from there, right? So we're going to have some level of balkanization of data, right? Like regions of sky where there's enough deep X-ray data and so on. And I think we'll just have to see what happens as we start to build stuff. Yeah, it's certainly a concern, but I think if we start simple and slowly but surely add on, features and data sets, we can handle that.
Okay. Here is a second question, I believe also from Michael. He says, you said that X-rays will be the ultimate tool for selection of AGNs. Does eROSITA go deep enough and have the angular resolution for the LSST AGN selection problem?
I mean, you could probably answer that better than I. I would say no to both of those. I'm more thinking in terms of sort of the Chandra deep fields. And so for example, the XMM LSS is providing a truth table for the training set. Yeah. I see eROSITA as providing data that will, then help us identify the AGNs and maybe in cases where the resolution isn't good enough or the depth isn't good enough, at least generate realistic probabilities.
Yeah, I would agree with that. I think that eROSITA is clearly going to be very helpful, but I don't think it is appropriately depth matched for the types of things we'll be going after with LSST, at least across the full sky region. That's just going to be very difficult. Okay, a couple of more questions here. Somehow the ordering is now changing, but in any case, I'll try to go through these. Here is another one. This is from Ilsang Yoon, asks, when you test the impact of features for AGN selection, did you optimize the selection threshold, for example, color, to maximize the performance in terms of TP and FN, which are the random forest terms?
Yeah, the true positives and the false negatives.
Right, yeah.
So I haven't done anything sophisticated, right? So everything, all the plots that I showed are literally just ones that Weizhang and I made in the last week for illustrative purposes for the talk, right? Everything is not ready in any way, shape, or form. But people that are interested in answering questions like that can basically access the training set as it exists, and you'll find that it isn't. It doesn't include everything that you would want and doesn't allow everything you want. But what we need is people to access the training set and tell us exactly that and where it comes short and give suggestions for how to resolve those problems.
Okay. Here's another question from Paula Sanchez. She asked, are low luminosity AGNs included in the current version of your training set? And if they are, how can she get them? She has interest in those.
Right. So no, because that's not the focus that we're starting with. That will have to be the case eventually. I think where that will start to become true is when we have constructed the training set and the XMM LSS area, where we have much better multi-wavelength data that we can use as truth tables for things that are much lower luminosity than the typical Sloan quasars that we're starting to focus on. But clearly recognizing the vast majority of the AGNs that LSST will discover are sort of low luminosity AGNs that don't look anything like Sloan quasars.
Right. Okay, here's another one. This one's from Swayam Panda, asks, does the dithering pattern affect the magnitudes in each band? And how much does this effect translate into the color selections? Does this relate to the DCR somehow?
Does the dithering pattern affect the magnitudes in each band? I'm not quite sure what's being asked. The DCR is independent of color. There has always been an issue with band passes not being observed simultaneously as they are in SDSS, although some recent simulations do have some bands being observed together. So the U and the G band, or the G and the R band, or the Y and the Z, and so on. And so that should help with colors at some level.
Here's another one. This is from David Westman. He says, you have not paid any attention to overlap with radio data. Can you comment on the need for help from the radio astronomy community? So I imagine this might include things like VLASS and ASCAP and MEERKAT and such.
Yeah, absolutely. So, I mean, I started to construct a spreadsheet for data ambassadors, and obviously, going in wavelength order, radio was the first thing on there first, and VLAS and MBSS, LOFAR, eventually EMU, WODON, right? So radio will clearly be crucial. It's just we haven't included it in the training set yet, although it shouldn't be too hard to add at least some first cut kinds of things.
Okay. And I'm trying to look through here. I believe those are the questions that we have. Training algorithm. Oh, here's one. Here's another one. Yeah, it asks, training the algorithm on SDSS data is not necessarily the best for LSST. How do we properly train the algorithm on LSST data?
Yeah, so I think I mean, my feeling is that we would like to take advantage of HSC data for that, and to have data that is going to look much more like LSST. And that will be something that we will get to, but haven't figured out exactly the best way to do that yet.
Okay, and I believe that's all the questions. And given that we are at time, I think we will stop the questions there. So first of all, thank you everyone again for attending, and I will remind you that there are 5 more sessions to go. So just the good stuff is just getting started here. The next session will be session number 117, which will be this afternoon starting at 2:50 p.m. So please, everyone is welcome to attend then if they have interest. Take care, everyone. Thanks a lot. See you this afternoon.